Let's talk about one of the most important pieces of technology you've probably never thought about. It's a tiny, unsung hero that's literally everywhere, but it's almost always completely invisible.
And we're going to start by uncovering a little bit of the magic that's hiding in the devices you use every single day. In fact, you've probably got one in your pocket right now.
I mean, have you ever really stopped to wonder how your phone screen knows to dim when you're in a dark room? Or how your TV remote sends that invisible signal across the room? What's actually happening there?
Well, the answer is a tiny, incredibly powerful light sensor. You can think of it as a microscopic eye, one that's constantly watching the world and translating what it sees, light, into pure information.
Okay, so how on earth does that actually work? Let's get into the science of it, how you can take a simple beam of light and turn it into a useful electrical signal that a device can understand.
So this is our hero component, the photodiode. You know how an LED works, right? It turns electricity into light. Well, a photodiode does the exact opposite. It takes in light, and we're talking the whole spectrum, from ultraviolet to infrared, and converts it back into an electrical current.
You know, the best way to picture it is as a tiny solar panel. But here's the crucial difference. A big solar panel on a roof is designed to generate as much raw power as possible. A photodiode is way more sophisticated. It's optimized for a very different job, accurately measuring light to carry information.
And the science behind this is, well, it's literally Nobel Prize-worthy. In fact, this is the discovery that earned Albert Einstein his Nobel Prize. It's called the photoelectric effect, and it's what proved that light can act like a stream of tiny energy particles called photons.
So the process itself is surprisingly simple when you break it down. First, a photon of light smacks into the sensor. Then, it transfers all its energy into an electron. And finally, if there's enough energy, that electron gets knocked loose. That flow of freed electrons, well, that's your electrical current. That's the signal our devices can actually read.
Of course, not all light-sensing jobs are created equal. You wouldn't use the same sensor for a smoke detector as you would for high-speed internet. So engineers have developed a whole toolkit of different photodiodes, each one specialized for a particular task.
First up, you can run them in two main modes. There's photoconductive mode. Think of this as performance mode. It's super fast, but it generates more background electronic noise. Then there's photovoltaic mode. This one is slower, but it's incredibly precise and quiet, which is perfect for measuring very faint, steady light.
And this brings us to the different flavors of photodiodes. You have your standard PN diode for basic jobs. The PIN diode is much faster, which is why it's used in things like fiber optics. The Schottky is for ultra-fast reactions. And then there's the superstar, the Avalanche Photodiode, or APD. This thing is so cool, it can actually amplify a weak light signal internally, letting it detect things that are incredibly dim.
So let's boil that down. It's all about picking the right tool for the job. If you need simple light sensing for a smoke detector, a basic PN diode works just fine. If you need the blistering speed required for the backbone of the internet, you're going to want a PIN diode. And if you need to see a very weak light pulse from far away, like for a self-driving car's LiDAR, that's a job for the ultra-sensitive APD.
On top of that, the actual material used to make the sensor is critical. Different materials are tuned to see different colors or wavelengths of light. Silicon is the cost-effective all-arounder, great for the visible light that we see with our eyes. But for the infrared light used in telecommunications, you need something more specialized, like indium gallium arsenide, or InGaAs. That's pretty much the gold standard for internet fiber optics.
Okay, so we've covered the science. Now let's zoom out a bit and look at how this tiny component has come to shape our modern world in just countless ways.
You know, this technology didn't just pop up overnight. It's a legacy of innovation that started way back in 1940 with Russell Ohl's discovery at Bell Labs. That work led to Junichi Nishizawa inventing that highly sensitive APD, and eventually to Yoshiaki Hagiwara's pinned photodiode, which is now the cornerstone of almost every digital camera sensor on the planet. So where are they? Honestly, everywhere. They're in your remote control, your smoke detector, they're in that little clip they put on your finger at the hospital, the pulse oximeter measuring your blood oxygen. They're in barcode scanners, CT scanners, and maybe most importantly, they are the receivers that make the entire high-speed fiber optic internet possible.
So when you really put it all together, you start to realize these sensors form this massive, interconnected network of invisible eyes that our entire technological world absolutely relies on.
If you take one thing away from this, it should be this.
These seemingly simple devices perform one of the most fundamental jobs in modern tech. They are constantly converting the physical world of light into the digital language of information, and that makes everything faster, smarter, and more connected.
And that just leaves you with a fascinating question, right? As these sensors get even smaller, even faster, and more sensitive, they're going to enable technologies we can't even imagine yet. So, what will our world's invisible eyes see next?